Welcome to BTS 2022. My name is Devarshi Chatterjee, and the topic of today's presentation is Fifo topology aware stalling for accelerating the coverage convergence of stalling regressions. This work is co-authored by Parth Latigara, Siddhant Dodi, and Chad Parsons at NVIDIA Corporation. In simulation-based design verification, there is usually a random test generator which drives stimulus onto the design under test, and the same stimulus is then also driven on a reference model. And then the output of these two are then compared to find out any discrepancies. Stalling is an important component of simulation-based design verification, where we artificially stall certain virtual channels and interfaces in the design to create congestion scenarios that are rarely seen. And this is done in order to expose deadlock bugs and other corner case bugs which are timing critical. Fifo-based stalling allows us to take this one step further by achieving fine-grained controllability over stalling internal interfaces and virtual channels in the design. To implement random Fifo-based stalling, we modify the FifoGen tool, which spits out the code for a vast majority of NVIDIA's Fifos. So after modifying this tool, we are able to insert custom stalling logic within each Fifo. And the finite state machine for this logic looks somewhat like the picture on the right. The key thing to remember here is that this stalling logic comprises of three stall parameter registers: the stall probability and the min-max duration of the stall. A Fifo can get into a stall mode only when a valid arrives. And the stall probability controls the probability that a Fifo will go into the stall mode when the valid arrives. And if it goes into the stall mode, then the stall is held for a time duration which is somewhere between the min-max duration of the stall. So the picture shows here is that a valid comes into the Fifo. The Fifo goes into the stall mode by reasserting the ready and then holds that stall for 8 clock cycle duration. The problem statement at a high level here is to decide how many Fifos do we want to stall in a test and what values should we program for the stall parameter registers in order to minimize the number of tests that are needed to achieve Fifo full condition on all Fifos in the design. So to achieve this goal, we have to design an objective function. And the objective function that we use here is the mean of the max Fifo occupancies across all Fifos and tests in the design. So to explain this situation better, let's use the example on the right. Let's suppose there are two Fifos in the design, F1 and F2, and there are two tests we ran, T1 and T2. Let's suppose that the Fifo occupancy of F1 in the test T1 varied a lot, but the max it hit was 50%. Similarly, the 40% is the max occupancy of F2 in the test T1. Now, if you look across tests, you will see that the Fifo F1 across tests hit a max occupancy of 100. Similarly, Fifo F2 hit a max occupancy of 60 across tests. So our objective will be the mean of the max, which is mean of 60, and 100, which is 80%. If you notice carefully, you'll see that the max value this objective can hit is 100%. And this will happen if all these numbers here are 100%. Which means the max, when the objective hits max value, you will find at least one, for every Fifo, you will find at least one test which has hit Fifo full condition for that Fifo. So in short, we want to do all these things assuming that tests are random and we do not know the stimulus a priori. And the other thing is we do not want to change the stimulus also because to achieve these conditions, because these tests that we're going to run are needed for feature verification and are vetted by coverage. So we just want to test the cross coverage of these tests run with random stalling enabled. So let's build up some intuition here by taking a simple example of a linear Fifo topology and trying to answer a question like how many Fifos should we stall and which Fifos should we stall. So in this simple case, we have 4 Fifos in a linear topology with data flowing from left to right. And we're trying to answer the question, how many Fifos should we stall? And the answer is clear that it's good enough to stall one Fifo. Because let's say if we stall F2 and F4 together in the same test at the same time, then the stall on F2 will block the data flowing into F3 and F4, preventing them from getting full. So due to this cross interaction, it's only good enough to stall one FIFO in a dependent data path. And because if we stall more, it will become redundant. And the question is, okay, if we're stalling one FIFO at a time, which is the best candidate and which is the worst candidate to stall? So again, you could see then that F4 is the best candidate to stall, because if there is sufficient data flowing in, then stalling F4 could fill up all other FIFOs in just one test. But is it good enough to stall F4 all the time? The answer is no, because we do not know how many data packets will come in. If there is limited amount of data coming in, then stalling F4 could stall F3. And maybe in another test, we stall F3, and that could stall F2. So the conclusion here is we have to stall all the FIFOs in different tests, but it probably is a good idea to bias the selection probability of stalled FIFOs towards FIFOs that are deep in the design. Now that we have an intuitive understanding of the problem, the next questions are, how do we extract this FIFO topology? And how do we generalize the conclusions that we made for a linear topology to a more complex topology, multi-tree type topology? And finally, how do we deal with multi-threaded FIFOs? This part we're not going to cover in this discussion. You have to refer to the paper for more details on this. Let me now try to address the question that how do we extract the FIFO dependency topology? It is worth mentioning here that because of the existence of virtual channels, it's not possible to extract this dependency topology from the netlist. And the reason is there could be two FIFOs sitting right next to each other and connected over the same physical interface, but one of the virtual channels might be blocked and the other one is not. So we cannot extract this using the netlist type data structure. So how do we really do this? And to answer that, I would refer our audience to the DeFiCon 2021 paper. But in this presentation, I'm going to give a very brief overview of how it is done. So at a high level, the idea would be to pause one FIFO at a time and see which, and let the traffic drain for a long time and see which all FIFOs or VCs get stalled behind it. And then we repeat this process by stalling different FIFOs in different tests and extract the information and combine them in a FIFO VC topology graph. So to give an example, let's suppose a design has two pipes, pipe A and pipe B, and in one of the tests we stall F3, and we hold the stall for a long duration of time. So the independent path drains out and the FIFO occupancies in the independent path become 0. So at the end of the test, when we see that the F1 and F2 cannot drain out, we can infer that F2 and F1 are dependent on F3. So we start drawing edges from F3 to F2 and F3 to F1. And then in different tests, we repeat this by stalling different FIFOs and combine all those information into a single graph to create this FIFO VC topology. Now that we know at a high level how the FIFO dependency graph is extracted, we're going to get back to answering the question that how do we select the stall set or the set of FIFOs to be stalled in a test in order to minimize the number of tests needed to fill up all the FIFOs in the design. So let's look at a typical FIFO dependency topology, which is like a tree structure. Here, the nodes are the FIFOs and the edges are the dependencies. So what that means is that if you stall one, FIFOs 2 and 3 could get stalled, and so on. And stall in FIFOs 2 can in turn stall 4 and 5, and so on. So the way this algorithm works, which we call the maximal reach through mutually non-reachable FIFOs, is that from the topology, first we compute the reach set of every node in the graph. So for instance, the reach set of node 2 is the number of nodes which can be reached from 2. So which is reach set of 2 is 2, 4, 5, reach set of 3 is 3, 6, and 7. After that, we find out the number of elements in the reach set of every node. And then we create a probability distribution which is proportional to the number of elements in the reach set. And based on the probability distribution, we do the first selection of stall FIFO. So let's suppose we throw a dice and using this probability distribution, select the FIFO. And let's suppose that the FIFO selected becomes 3. Since 3 is selected, we include 3 in the stall set, and then we remove all elements in the reach set of 3 and all elements which have 3 in its reach set from the graph, and prune the graph accordingly. So now we have a remaining section of the graph, and we repeat the process on the remaining section. And let's suppose that by repeating the process using the new probability distribution, we select the element 9. Since 9 is selected, we include a 9 in the stall set and remove all elements which are in 9's reach set, which is 8, and all elements which have 9 in its reach set from the graph, and then repeat the process on the remaining section of the graph with the new set of probability distribution. And let's suppose now the node selected to be in the stall set is 4. So 4 now gets included in the stall set, and node pruning needs to be done because there's no element in the 4 reach set and no element which has 4 in its reach set which are already not pruned. So the only point remaining is 5, and in the next round 5 will get selected in the reach set in the stall set. So we now have the final stall set selection, which is the number of FIFOs that we're gonna stall in a particular test. For a different test, we repeat the process again, find a new stall set, and stall those FIFOs. At a high level, if you look at this algorithm, what we have done is that we have made sure that the number of the FIFOs that get selected in the stall set and the selection probability is higher for FIFOs which are deep in the design. And the other property of the stall set is that for every pair of FIFOs included in the stall set would be mutually non-reachable in the FIFO topology. And what that does is that it basically reduces the cross interaction of stalling between the FIFOs. And these are the two properties which intuitively we learned from linear topology, that they are good candidates for stalling. The figure on the right shows the output of the algorithm for stall set selection that I just described, which applied on a real FIFO dependency graph extracted from a small section of NVIDIA's design. And you can see the green nodes are the FIFOs that are included in the stall set. And you could see that for every pair of node in this graph, every pair of node is mutually non-reachable. Now that we have discussed the method to select the stall set, let's now go into answering how do we select the stall probability. Just to recall, a stall probability is one of the stall parameter registers within the FIFOs, which decide the probability that a FIFO will go into a stall mode on the arrival of a valid. And usually, the general approach is to use a single small value of stall probability across all the FIFOs. And the problem with that is that there's a lot of variability of FIFO activities across the number of FIFOs. Like most of the FIFOs have around 200, 300 valid in a test, but there are some FIFOs which have very low activity and some which have very high activity. And using a same stall probability basically makes the low activity FIFO very hard to stall, and a very high activity FIFO gets stalled too frequently, causing a lot of test timeouts. So what we did is we did some statistical analysis to find out that even the low activity FIFOs basically show some variations across tests. So the low activity is the blue FIFO, and it shows quite a bit of variation across tests. Similarly, medium activity FIFOs also show variation across tests. So what we do is, instead of using a small value, same value of stall probability for all FIFOs, we collect some statistical data and set the stall probability using the formula PS over K over mu, where PS is the stall probability, mu is the mean activity of the FIFO across the tests. And just by doing so, we make sure that the expected number of stall for each FIFO is K, which is K is of the order of 1 and 2, irrespective of whether the FIFO is high activity or a low activity FIFO. In the interest of time, I cannot go into too much details about how we do the computation for the min-max stall duration for each FIFO. But at a high level, I would say that we collect statistical information about the mean arrival rate, mean arrival duration of valids on every FIFO, and then use that information along with the information about the depth of the FIFO and how the FIFO is located in the FIFO dependency structure to compute the min-max stall duration, which would stall or fill up not just that FIFO, but all FIFOs in the subtree rooted at the stalled FIFO. So we compared our method of stall set selection and stall parameter selection with the random scenario selection that we have currently in place. And we found that our method boosted the mean occupancy, the mean of the max occupancy by 43%. And the number of unique FIFOs that were boosted by our method was 6%. And all these numbers were computed over a set of 200 tests, where the average runtime of our tests were much smaller than the random scenario tests. Okay, so far we have established that using our scheme, we actually improve the coverage metric over the existing scheme. But the question we really need to answer is how many extra tests using the old scheme do we need to run to get to the same coverage boost that we got? And to answer that question, we compare the coverage convergence of these two schemes. So on the x-axis, you see the number of batches of tests being run, each batch being 50 tests, and on the y-axis, the coverage metric, the cumulative coverage metric. So the yellow dots here show the coverage convergence with our scheme. And as you can see that after 30 batches of tests, we hit 90% coverage objective. And by extrapolating the existing scheme, we see that the same 90% would need about 70 batches of tests. So from this, it can be seen that our scheme accelerates the coverage convergence of stalling regression by a wide margin. In conclusion, I'd like to mention that in this paper, we present a white box approach to select stall set and stall parameters. And to do that, we just need to reuse the FIFO VC topological information captured in the FIFO dependency graph, which we generate anyways for analyzing cross dependencies for deadlock avoidance. And the only additional data we need to collect is the minimal statistical information about the FIFO activities and the arrival durations. And by doing so, we basically reduced significantly the number of tests needed to hit FIFO and all FIFOs in the design. Thank you for listening to my presentation.